Welcome to the deep dive. Today we're tackling something fundamental. How do you make sense of things when, well, everything seems to depend on lots of other things? We like simple cause and effect, but reality, it's usually way more complicated.
It really is, and that's exactly why we're diving into multivariable and vector functions today. And look, this isn't just abstract math for its own sake. It's really a way of thinking, a framework for understanding systems with many interacting parts.
Yeah, like, well, almost everything interesting, right? Economics, physics, biology.
Exactly. Or even just figuring out the perfect cup of coffee temperature, grind size, brew time. It all matters.
Okay, so our mission today, take a chapter from a math textbook, something that might look a bit intimidating, and pull out the key ideas. We want to help you understand how to describe, visualize, analyze these functions that go beyond just YFLFX.
Think of it as a shortcut to getting really well informed about a concept that pops up everywhere.
We'll be drawing insights directly from this textbook material on functions of several variables in three-dimensional space.
Yep. And the goal is to make it accessible, maybe even spark a few aha moments. Without getting bogged down in excessive jargon, we want you to leave with a richer way of seeing how interconnected things really are.
Great, so let's start simple. We all remember y if x, right? One input x, one output y, easy to graph on a piece of paper.
A nice line, a curve, familiar territory.
But what happens when your outcome depends on more than one thing? When it's not just x driving the result, but maybe x and y, or even x, y, and z?
That's exactly when we enter the world of functions of several variables. And this is where things get, well, much more interesting and powerful.
Okay.
Think about compound interest. The final amount in your account, A, doesn't just depend on the initial principal, P. It also depends, crucially, on the time, key, it's invested.
Right, two key ingredients.
Exactly. So A is a function of both P and T. We might write it as APT.
Okay, so A is the result, and P and T are like the ingredients that both determine the outcome?
Precisely. It's not just one cause anymore. It's multiple factors working together. We can have functions of two variables, like the interest example, or three variables, maybe something like fxyz equals by 2 big C plus cos,
Okay.
or even n variables. The math lets us handle situations where a whole list of factors determines a single outcome. It assigns a unique number to an ordered list, an n tuple, like by 1 by 2 xn.
So this framework actually lets us model things that are, realistically complex.
That's the beauty of it. It starts to mirror the way the world often works.
Here's where it gets really interesting, though. What about the domain of these functions? It's not always any number you want, is it? Like, there must be limits.
Absolutely critical point. The domain is the set of all possible input combinations for which the function actually gives you a valid output, or is mathematically defined.
So the operating rules.
Kind of, yeah.
Yeah.
Let's take an example from the text, like qxy, x plus y by 2y2.
Okay, a fraction.
Right. And what's the main rule with fractions?
The bottom part, the denominator, can't be 0.
Exactly. So x2, y2 cannot be 0. And that happens if xy or if x equals y.
Ah, okay, so those combinations of x and y are out.
They're excluded from the domain. They represent lines on the z-plane where the function just breaks down. It's undefined.
So the domain isn't just a range of numbers, it can be a whole area with specific boundaries or exclusions.
Precisely. Or consider another one, sxy equals 1 squared is 2, 1 by y.
Okay, square root this time.
Yep. And what do we need for a square root to be defined with real numbers?
The stuff inside has to be non-negative, and since it's also in the denominator, it actually has to be strictly positive, right?
Okay. So 1 die must be greater than 0?
Which means xc must be less than 1.
Right. And think about what that looks like on the z-plane. It's not a simple line. If x and y are both positive and large, or both negative and large, their products xc could easily become 1 or more. So those regions are excluded. The domain is this specific area where x1.
Understanding the domain feels like understanding the rules of the game. When does this mathematical model actually apply?
That's a perfect way to put it. It defines the operational boundaries. When does the system work and when does it not? Knowing that is step 1.
Okay, so we've got functions with multiple inputs working in these potentially complex domains. If we move beyond a single input x, we can't just draw a line on flat paper anymore. How do we visualize these functions?
Yeah, our 2D toolkit needs an upgrade. We move into 3 dimensions. We add a z-axis, sticking straight up, perpendicular to both the x and y axis.
Like the corner of a room.
Exactly like that.
Yeah.
The book mentions the right-hand system to keep things consistent.
Yeah.
If you curl the fingers of your right hand from the positive x-axis towards a positive y-axis.
Your thumb points up the positive z-axis. Got it.
So here's the key insight. The graph of a function of two variables, fx, y, isn't a curve anymore. It's a surface floating in this 3D space.
A surface.
Yeah, think the z-plane as the floor. For every point xy on that floor, the function calculates a value, zfxy. That z value is the height or altitude above or below that point on the floor.
Oh, wow. Okay.
The text has some great visuals. For instance, fxy equals squirt by 2 plus y2. What does that look like?
By 2 plus y2 reminds me of circles, square root, maybe a cone.
Bingo. It's a perfect cone, starting at the origin and opening upwards. Or another classic, z equals by 2 plus y2. That forms a smooth bowl shape, a paraboloid.
So what does this all mean? We're literally giving depth to our understanding, mapping the output as a height or depth.
Exactly. We're mapping a landscape. It could represent actual terrain altitude or temperature distribution across a surface, or maybe pressure fields inside something. You give a tangible shape to the function's behavior.
And how do we even measure distance in this new 3D world? Is it just like regular distance?
It's a really elegant extension of what we already know, the Pythagorean theorem.
Ah, a2 plus b2 equals c2.
Right. In 2D, the distance between x0, y0, and x1, y1 involves s1 by 02 plus y1, y02.
Yeah.
In 3D, we just add the third dimension. The distance between px0, y0, 0, and qx1, y1, 01 is the square root of t by 1 by 02 plus y1, y02 plus z1, 02.
Okay, that makes intuitive sense. Just add the square difference in the z-coordinates.
Yep. And this distance formula is super fundamental. It immediately gives us the equation of a sphere.
How so?
But what is a sphere? It's all the points that are the same distance, r, the radius,
Right.
from a center point, x0, y0, 0, 0.
Right.
So using the distance formula, we set the squared distance equal to r2. That gives us x by 02 plus y02 plus z02 plus 02 equals r2. That's the equation for a sphere.
Ah, derived straight from the distance idea. That's neat. And this geometric foundation, it must be everywhere.
Oh, absolutely.
Yeah.
Computer graphics rely heavily on this, defining shapes, calculating viewpoints. Same for physics, engineering, astronomy.
Yeah.
Understanding spatial relationships in 3D is built on this.
Okay, 3D graphs are fantastic, giving us this overall picture, the surface. But sometimes you need to dig deeper, right? Understand specific slices or features of that surface. How do we zoom in?
Great question. We use two really powerful tools for that. Traces and level curves.
Traces and level curves, okay?
Let's start with traces. Imagine taking a knife and slicing straight through your 3D graph parallel to one of the coordinate planes.
Okay, like cutting a cake vertically.
Exactly. Mathematically, you do this by fixing one of the input variables to a constant value. Say you set y equals c, some specific number. The equation then becomes z equals fxc. Now z only depends on x.
So you get a 2D curve again.
Yes, but it's a curve lying in that specific vertical plane where y is c. It shows you how the function behaves along that particular slice. You can take traces parallel to the yz plane too, by setting x equals c, giving z equals fcy.
Let's make that concrete. The book used a projectile motion example.
Yeah, distance d depends on initial velocity x and launch angle g. So d equals fx, g. If you fix the angle, say g equals 0.6 radians, you get a trace d equals f(x) equal 0.6. This turns out to be a parabola showing how distance changes only with velocity at that fixed angle.
Okay.
But if you fix a velocity, say x 1,250 feet, you did d equals f150g. Now you see how distance changes only with the angle, which looks like part of a sine wave.
So by fixing one element, we can isolate and really see the impact of another. That's incredibly insightful for cause and effect, like running a controlled experiment mathematically.
You nailed it. Now, the second tool, level curves.
Okay, what are those?
Think about a topographic map, a map of mountains and valleys.
Right, with all the contour lines.
Those contour lines are level curves. Each line connects points that have the same elevation, the same altitude.
Oh, okay.
For a function s(xy), a level curve is the set of all points, xy, down on the z-plane, the map, where the function's output z equals xy is equal to some constant value, k. So fxy, k.
What's fascinating here is we're flattening a 3D surface back into a 2D map, but we're still capturing its shape, its essence, like a blueprint. You can see where it's steep, where it's flat.
Exactly. You're projecting the 3D shapes onto the 2D floor, but encoding the height information using these curves. Look at the examples in the text again. The paraboloid z equals by 2 plus y2. Its level curves by 2 plus y2 equals k are just.
Circles, concentric circles, makes sense. It's a round bowl.
Right. But now look at the saddle surface. Z equals by 2, y2. The level curves by 2, y2, I equals by 0. You get lines xy and xy.
Whoa, completely different pattern, even though it's also a smooth surface.
See, the level curves instantly reveal the underlying structure. They show you the topography of the function. One looks like a hill, The other looks like a mountain pass or a saddle.
That's a really powerful way to visualize.
And just briefly, if you have a function of three variables, f, x, y, z, you can talk about level surfaces. These are surfaces in 3D space where the function's output is constant, f, x, y, z. Think of regions of constant temperature or pressure within a volume.
So traces give you cross-sections, level curves give you a contour map. Both help dissect these complex
They
functions.
reveal patterns you'd never see just by looking at the equation or even the full 3D graph sometimes. Think weather maps, isotherms are level curves of temperature, isobars are level curves of pressure. Absolutely vital.
Okay, this raises an important question. Beyond the abstract math, where do we actually see these multivariable functions influencing our daily lives and scientific breakthroughs? Let's bring it home.
Oh, they're everywhere once you start looking. The textbook gives some great examples in the exercises. Take the ideal gas law. V, nRTP. Volume V is a function of pressure P and temperature T.
Right.
So a trace where you hold temperature constant shows you how volume changes with pressure Boyle's law, basically.
Mm.
A trace holding pressure constant shows how volume changes with temperature Charles's law.
And level curves.
Level curves would be curves on a PT diagram showing all the combinations of pressure and temperature that result in the exact same volume. Super important in chemistry and engineering.
Okay, what else?
Think about car loans. The monthly payment, M, depends on the interest rate R and the loan duration T. So MSMRT.
Imagine how practical level curves would be here, helping you find different interest rate or duration combinations that result in the same affordable monthly payment.
Exactly. You could literally see, okay, if I want my payment to be $350, I can have this rate for this long or this slightly higher rate for a shorter time. It maps out your options.
That's very useful. Any others?
How about drug concentration in the body? The concentration C depends on the dose X and the time T since it was administered. C equals FXT. Doctors and pharmacologists use these kinds of models constantly.
To figure out dosages and timing.
Precisely. Traces show how the concentration changes over time for a given dose. Level surfaces might show combinations of dose and time that keep the concentration within a desired therapeutic window, not too low, not too high. It's optimizing treatment.
So this framework lets us model, predict, and optimize outcomes in all sorts of real-world situations. It's about seeing the connections.
It really is. It's the language for describing how multiple factors weave together to produce a result.
This isn't just theory, it's the language used by scientists, engineers, economists, doctors, people trying to understand and manage complex systems every day. We've covered quite a journey today, haven't we? Started with simple functions, realized we needed more inputs.
Yeah, moved into multiple variables,
Then figured out how to visualize these as amazing 3D surfaces.
giving them shape and form.
And then developed tools like traces and level curves to really analyze the details, the patterns within those surfaces.
It's a powerful progression, building up the toolkit.
And the big takeaway seems to be this framework for thinking critically about systems where lots of things are happening at once.
Absolutely. It's about appreciating interconnectedness, moving beyond simplistic explanations, and having the tools to actually analyze that complexity.
So what does this all mean for you, listening right now?
Well, understanding multivariable functions helps you grasp how complex systems work, whether it's the economy, the climate, or even just a project you're managing. It empowers you to ask better questions when someone presents information where multiple factors influence an outcome.
It encourages a more nuanced view.
Exactly. Moving beyond A causes B to A, B, and C interact to influence D in this particular way. It's a richer, more accurate way to see things.
So here's a final thought to chew on.
Think about a complex issue you're interested in, and maybe planning your personal finances, understanding climate model predictions, or even optimizing a process at work. How many variables are really involved? Can you imagine what the traces might look like if you held one factor constant? What might the level curves, the combinations leading to the same outcome reveal? What real-world surfaces are out there waiting to be mapped and understood in more dimensions than we usually consider?
It's a challenge to start seeing the world through this multi-layered lens.
But it's incredibly rewarding. We hope this deep dive gave you some tools and inspiration to do just that.